Hello everyone, my name is Elijah Proctor, and today we're going to talk about how Python can be used to diagnose and address violations of assumptions in linear regression models. And so here we have a data set that simulates the performance of 100 players across 20 games. It records the total minutes each player played and the points that they scored. And the resulting data set has 2,000 rows where each row represents a player's performance in a single game. And so this generates a 20 by 100 matrix. And so we use our flatten function so that it turns into 2,000 rows. So we have our minutes and our total points for these players. And we're going to store this in this data frame. And then we're going to fit a linear regression model to the data, calling this ordinary least squared function. And this is a formula that specifies the model. And so for our independent, or for our dependent variable, we have our points. Our independent variable is our minutes. And then we're going to pass in game data and make sure we call this fit function. So make sure we fit the model. And then we're going to add predictions from the linear model to the game data. And so we're going to store our model linear.predict function and pass in our game data minutes, and we're going to store this inside of our linear prediction array. Then we're going to compute the residuals, which is the difference between observed and predicted points. And so we have this is going to be our game data points minus our game data linear predictions, and we're going to store this inside of our linear residuals. We're going to plot the residuals so that we can check to see any patterns, any non-linearity. And so we're going to plot this using a scatter plot. We have our x-axis, which is our minutes played. Our y-axis is our residuals. And we're going to then perform statistical tests to see model assumptions. And we're testing here for normality of residuals using a Shapiro-Wilk test. And so we're going to call our stats.shapiro function, pass in our linear residuals, and we're going to store it inside of this test results variable, and then display the results. Then we're going to test for homoscedasticity using the BP test. So we're going to call this BP function. We're going to pass in our residual ID and any relevant comparing variables, and then we're going to extract the p-value from the BP test results, which is just our BP test at index 1, and then we're going to display that result. And so if linearity assumption is violated, we can try fitting a polynomial regression model. And so first we need to calculate the minutes squared for all of our minutes, store it inside this array. Then we're going to fit a polynomial model to the data using our ordinary least squared function. And so our formula has our points as the dependent variable and our minutes and minutes squared as our independent variables. And then we're going to make sure the model is fitted correctly. And then we're going to add a polynomial model predictions to the data frame. And so this is just going to be equal to model polynomial.predict, passing in our independent variables, minutes and minutes squared. And then we're going to compare the models by calculating the mean square error. And so this is going to be our points minus our linear prediction squared. And then we're going to find the mean value of that. We're going to do that for our linear and also our polynomial model. And then we're going to print those results. And then we're going to show the first few rows of the data frame so that we can verify the results. And so here we have our scatter plot, which shows the results of the linear regression analysis on the basketball game data. And it displays the residuals, which are the differences between the actual points scored and the points predicted by the linear model. And this is plotted against the minutes played. And so the fact that the residuals seem evenly distributed around this horizontal line, this blue horizontal line, it suggests that the linear model is appropriate for this data, and it means that the relationship between minutes played and points scored is likely to be linear. And so here down below we have the results of statistical tests and error calculations. And so the Shapiro-Wilk test has a p-value greater than 0.05. This indicates that the residuals are normally distributed, which is a good sign for validating the linear model. And for the BP test for homoscedasticity, this also has a p-value greater than 0.05, and this suggests that the variance of the residuals doesn't change with the minutes played, which is another good sign for the validity of the linear model. And so our mean squared error values for both the linear and polynomial models are exactly the same. And so this basically is saying that adding a polynomial term, which is our minute squared, this doesn't significantly improve the model's accuracy. And so basically the linear model seems sufficient for predicting the points based on the minutes played. Thank you guys for listening. That is all.